So I'm going to just quickly go over that and give you some examples here. So again, when we're talking about alpha radiation, if we have polonium, and this is an example that we already worked, but just to give you a refresher again, if we have polonium, where's my notes? They're on the laptop here. There you go. Okay. 208, mass number, 84 as our atomic number. And we have alpha decay. So what do we get from alpha decay?
Helium.
What?
Well, it takes away helium.
So it splits off into a helium nucleus, right? So that's going to look like this, and then what's on the bottom?
2,
Top?
4.
Yep. And then what are we left with?
Lead.
We're left with lead. Specifically, what's the atomic number and mass number?
204 and 82.
82, all right.
204.
And then 204 on the top.
How are you guys getting those numbers?
Subtract 2.
Okay, because the arrow's like an equal sign, right? And so top numbers have to add up, bottom numbers have to add up. Law of conservation of mass.
All right, so we understand alpha radiation. For alpha radiation, how far does alpha radiation penetrate? Like, how can we stop alpha radiation?
With a sheet of paper.
Yeah, just about anything. Sheet of paper, your skin can even stop it as long as it's not exposed.
Stop for lunch.
Open back.
You may be late. I know, but you stop for lunch on the way home from our
Yeah, they haven't told us the bell schedule all. Like, our C3 kids, the past 2 days have just been purely guessing on where to eat lunch. Like, yesterday I didn't know where to eat lunch.
Anyway,
I just,
just for the record, class starts at 11:50,
Yeah.
and we eat lunch, which means 1:35. So everybody is very jealous of you.
Madison, go ahead and get your fill-in notes. We're reviewing the 6 types, or the types you've already covered, and then we'll go into the rest of the types of decay.
Oh, we have an hour and 40 minutes.
Yeah.
I think I might pass out in the class.
I love this.
Yeah, that's why it's important to bring a snack, especially this late in the day. I mean,
No, I just eat a muffin for breakfast and then nothing else for lunch. Yes. And then
So,
a glass of water.
just to quickly cover, for Madison's sake, we just kind of talked about our formula for alpha decay, and then we talked about how basically anything can stop alpha radiation. You can have like your skin can stop it, like a piece of paper can stop it. And that's just because, I mean, like, if you look at this, I mean, helium, and a helium nucleus is going to be much larger than the rest of the radiation that we're going to talk about today. So it doesn't really penetrate as far as other types of radiation. Yeah?
Maybe a dumb question. It's just helium. How's that harmful? How can it be harmful if it's like just helium?
I heard half of that. Sorry.
If it's not, or like it's just helium, how can it be harmful?
If it's just helium, how could it? Okay, I heard helium.
How
and
can
then
it be harmful?
How could it be harmful? Okay. It mainly just comes down to when you have alpha decay, it releases energy, and it can mainly cause harm if it's inside the body, because you've got a bunch of different. If you have a bunch of this going off at once, you're going to have a bunch of different energy. It's going to affect a lot of the cells inside the body. And we'll get into that further when we talk about the effects of radiation on the body. Particularly, we're going to kind of focus on, or at least the focus we're going to use is polonium-210, because it was used in a very recent and very famous assassination. And the main reason behind that assassination is because polonium-210 likes to give out a lot of alpha decay, and it affects the body on the inside. So we'll talk about that a bit more. I don't know if we'll get to that today, probably tomorrow. But it'll kind of explain, I have a video, it'll kind of explain what that radiation does to the cells inside and why it ends up turning them cancerous. Yeah. Sorry, it's a vague explanation for now, but we'll get into it later. All right. So that's alpha radiation. So again, we're going to go into beta radiation. So from beta radiation, remember what happens in beta radiation. So, and this is a nice.
Oh, it's like where like the neutron splits into a proton and electron and it shoots it out in the nucleus.
So the neutron splits apart into a proton and electron, and then shoots what out from the nucleus? An electron, right? Yeah. It doesn't shoot out the proton. So what happens is that you get the neutron that splits up, the electron gets sent flying. So that's why we use the E greater 10 when we talk about that, right? So let's do a little formula here. This is kind of what we covered. Did we get to? I feel like we got to talking about beta decay, but we didn't go over the formula for beta decay.
Yeah.
You get the part where it
We
shoots
only
out
did
the
the
electron and
definition.
that's it.
So we only did the definition, we didn't get the formula. Okay, so
We didn't do anything else.
gotcha.
A neutron is
So
turned
I
into a
wrote out
proton
this-
and an electron.
As just a way for us to represent an electron when we're dealing with nuclear radiation and nuclear decay. We'll write it out like this -1, 0 E, because again you're releasing one electron from that whole system. So let's write a beta decay formula. So you can see that in the first part of the notes here, where we have carbon-14, pretty famous, very unstable isotope here. So yeah, beta. And it's important to
No,
note
just
with
the
beta
definition.
decay, we're going to use beta minus here because there's an alternate form of beta decay that we'll talk about in a bit. That's beta plus, and that one's a little weirder. Yeah.
Oh, we didn't do the smaller, faster one. We didn't, can be stopped by for beta part.
Oh, the rest. Yeah.
Mhm.
That's right. Let me pull this out. I probably better. Yeah, because y'all said we didn't even go over the notes.
Nucleus not.
I should have turned this on beforehand, but now I'm gonna wait. So I guess to talk about this, let me make sure we have a fill in notes. So as I said, the nucleus. Let me check and see if this is a note thing that you fill in. Yeah. Okay. So part B. So for B here, whenever it loads up, we said that a neutron turns into a proton and electron, and the electron gets emitted. So where's the electron? What location is the electron coming from? If it's coming from that neutron being changed, comes from the nucleus, right? So it's different than the electron cloud. So that's part B. Essentially, what we're looking at is, that electron's not coming from the electron cloud that's around this atom here. It's coming straight from the nucleus, from that splitting of a proton or a neutron into a proton and electron. So. Oh, let's do it this way because it's easier to write it in. Not easier, but it looks. There you go.
Wait, what?
Alright, so. Good, like we said, electron emitted. I'll get used to this eventually. The electron is emitted from the nucleus, not the electron cloud.
I always misspell nucleus. I don't know why.
Yeah, that doesn't look like an E, but here. It still doesn't look like an E.
I get the U and the E confused sometimes and just put nucleus.
But yeah. So yeah, kind of like what we already mentioned, when we think of a neutron, we think of basically a proton and electron just combined into one, which is why the neutron weighs slightly more than the proton. Kind of mentioned right briefly at the end of class, if you all remember that. So smaller, faster, more energy antiparticles can be stopped by. So basically, so we know that alpha radiation can be stopped by practically anything. Beta radiation, or beta decay, the particle's a little bit smaller, so does it make sense that we would need something a little bit more to stop beta radiation, or beta decay? I keep saying radiation decay like they're interchangeable, but yeah. So we can stop beta decay by like a 1-inch piece of wood. So you wouldn't necessarily be able to stop it with just skin, but one piece of wood could work. If you were wearing really thick clothes, that could also potentially stop beta decay. Although I think that more depends on the material of the clothes themselves. But again, it's a little bit more penetrating, a little bit more faster, but it's just not as effective, or it's not as penetrating as other types of decay on this one. Did somebody raise their hand? I swear somebody did. Maybe I'm crazy. Okay, I'm crazy. That's that's good to know. And then finally for F, so if beta decay comes from a neutron splitting into a proton and electron, what types of elements do you think beta emitters would come from? Like what subatomic particle would there be in excess? Neutrons, right? Yeah, neutron-rich elements is what we're going to say. Yeah, neutron-rich, or neutron-rich isotopes, rather.
Yeah, I know, they're going.
Right, because again, we have too many neutrons in a system. It makes sense that if an atom's unstable and we've got too many neutrons, that one of them might want to not be a neutron at some point, right? Which is not the scientific term, it's just not want to. But that kind of makes sense, right? So I think we mentioned this at the beginning with the fill-in notes. There's the ratio between how protons and neutrons want to exist in elements. Do y'all remember that from the first page of notes? I think that's in the first page of notes.
1 to 1.
Yeah, so smaller elements is 1 to 1, and larger elements it tends to be 1.5 to 1. So this is kind of a way you can kind of tell beta emitter, right? Because let's take that example that I tried to mention here with carbon. Yeah, I'm about to. So let's take that example for carbon 14, for example, right? So carbon fairly small, so you think it's stay pretty tightly to that one, or want to stay pretty tightly to that 1-to-1 ratio, right? And we kind of see that with like the normal forms of carbon, right? Because normal form of carbon is 12,6C, right? But when we have carbon 14, it's unstable. One of the reasons why it's unstable is because it's got that, it's above that ratio, so it's way more neutron rich. So carbon 14 likes to undergo this beta emission. And then, oh, there's the graph. Yeah, so this is a graph kind of, I think that's in your book, page 651. It's kind of, this is known as a band of stability. So you've got number of neutrons on the top, number of protons at the bottom. So it's just showing what that ratio looks like for all these different elements here. So it's a nice little graph, just kind of show these different, the different ratios here.
Notice how 1 through 20 follow that bottom red line, which is the 1-to-1 ratio. But the more protons, after 20 protons, you start needing more and more neutrons to keep it stable. So it starts leaning up towards more neutrons until you get to the very heaviest elements, to where then it's a 1.5 to 1 ratio. In other words, 3 neutrons for every 2 protons. Okay? So the more protons you have, the more neutrons you need to kind of stabilize it. If you're outside of that stable band, then there's radioactive. Okay.
And so we'll talk about kind of the, not the polar opposite, but reverse of this, because I guess the second question that would come to mind is like, well, what if there's less neutrons than the proton ratio? And I think that might be a question that comes up.
It explodes.
It explodes? It doesn't explode. But we'll talk about that kind of decay in a second as well. So, we gotta move this out of the way. But that's more of a spoiler for the one of the next one. So let's go for examples here. So like I mentioned earlier, you've got this carbon 14 here. It undergoes beta decay here. And that's a negative, not a positive. It kind of looks like a plus here, but that's a beta negative. And you get this formula, which is the electron getting emitted, and then you get this nitrogen 14 here, right? So what happened to the atomic number?
Atomic number increased by 1.
Increased by 1. Why did it increase by 1?
Because it lost an electron.
It lost a proton?
It added a proton.
It added a proton. Well, more necessarily, it converted a neutron into a proton. So you got a proton electronegative, and then the atomic number, words. The mass number here doesn't change. So why do you think the mass number doesn't change, right, if we lost a neutron?
Because aren't the proton and the neutron like the same mass?
The same mass, yeah, exactly right? Or they're close to the same mass, right? So even though we've technically lost one neutron, right, we've gained a proton in that sense. So if you're losing one and gaining one, your net is what? 0, right? So that one's a little bit weird, and that's why it's kind of hard to see that at first. But just remember, like, even though we're losing a neutron, you think the mass number goes down, but remember, the mass number is number of protons plus number of neutrons. We lost one neutron, gained one proton, so our net result for our mass number is not going to change. So that's what we're going to see in beta radiation. All right, so now just to fill an example here, we've got this calcium-45. It undergoes beta decay. What are we going to get?
45
20.
on the top and 21 on the bottom.
For here, so all right.
SC. Oh, not for that one, but
So 45, 21. What is this element going to be?
SC. What is it?
SC. I think it's
Scandium.
scandium. Yeah. I don't remember all the periodic table. Mr. Hobbs remembers way more of it than I do. So 45, 21 scandium, and then what are we going to have here?
0, -1.
A 0, -1 electron, right? Does that make sense for doing these beta emissions? Okay, awesome. So we'll go ahead and erase this. We'll move on to gamma, which is the other one that was mentioned in the video, the other form of radiation.
Wait, okay, maybe the second. For everyone.
So gamma radiation, it's high energy radiation similar to an X-ray. So I'm just going to give you this one because they kind of mentioned it in the video, but similar to X-ray, but emitted from the nucleus. So that's important to know this here. Do you remember in the video what gamma radiation emits?
Energy.
It's just energy, right? Do we emit any kind of subatomic particle from gamma radiation? No, right? So it is just energy here. It's not what's the exact word we're going to use in the filaments because I want to make sure that you don't have the exact words. Yeah, not a part. Yeah. Important thing to mention with this is that it's usually emitted simultaneously with alpha or beta decay, and that's what you'll see with a lot of different decays is that you're not necessarily just going to get one type of emission. For example, and we'll go over this when we go over like the atomic bomb. But when an atomic bomb releases, usually let's say 235 uranium, that's 92. I don't know if it's 92 or not. Is it 92? Right? Are we that right? Yeah. So when this ends up radiating or releasing radiation, and we'll get into what this does. It does spontaneous fission, which means it splits apart into different atoms and releases some neutrons. But it also releases gamma radiation because the isotope itself is highly energized, and so when gamma radiation occurs, it basically goes from this excited energy state to like a normal energy state. Of course, this is not like what happens with the road on the one side. I wrote this on the wrong side too. One more time. So this is, I mean, not necessarily a great example because we know that uranium is going to end up splitting up. We'll see that later. But with gamma radiation, which this is the symbol we're going to use here, you're basically going from a higher energy state to a lower energy state. These are really excited. This is a really excited isotope. Gamma radiation occurs where it releases that energy from the nucleus, and you get the lower energy state, which is why I should have written that there. Does that make sense for gamma radiation? You're really not changing anything. It's just the energy state or level. So we usually denote that with this little asterisk right here.
Isn't it just, it's like the part, there's like bouncing off each other, being like it's just like bouncing off each other and then like it just shoots out the energy?
It's just highly energized, so it's not necessarily that it's I'm trying to think of the best way to explain this. It's just extra energy that's inside the uranium ion. It's from the nucleus, right? So if we're thinking about energy from the nucleus, if I'm remembering correctly, it should be, you know how we have the nuclear binding energy, right? So there's a certain amount of energy that we need in order to keep the nucleus together, right? So in a highly energized state, we have excess of that, and so it ends up getting released at some point as gamma radiation. Okay. You like rose your hand for a second, I saw it in front of you.
No, well, maybe I did. I don't have a question though.
Oh, okay, gotcha. But yeah, that's essentially what gamma radiation is. It doesn't change the neutron itself. It's just a highly energized nucleus going to a lower energized nucleus, and so it releases that extra energy into the environment. Gosh, these bells are annoying now. So, if we're talking about gamma radiation, and this is just straight energy, right? So we know that it's going to be able to penetrate pretty deeply, right? As far as how deeply that goes, it's about 3 feet of concrete. Let me double check again. 3 feet of concrete. And this is why stuff like Chernobyl and like any kind of nuclear disaster is so dangerous, is because of these gamma radiation particles, because it pretty much permeates your entire body. Because it's, unless you're in a safety bunker, like, you're not getting away from gamma radiation if you're close to it. Alpha radiation, I mean, obviously if you don't have cuts on your skin or anything like that, you're getting away with not getting affected by alpha radiation, unless it goes inside your body through like your nose or something like that. Beta radiation, a little bit more dangerous, but you can somewhat avoid beta radiation. Gamma radiation, almost impossible to avoid unless you've got that serious protection. Yeah?
Will they use to like treat cancer patients?
The treat cancer patients, I'm glad you asked this, because we're actually going to go into that. You actually fight cancer with radiation, and so we'll talk about why that works and why, specifically, why treating it with radioactive elements doesn't kill you over the cancer, if that makes any sense. I found some fun videos for that, and we'll get into that probably tomorrow, because I don't think we'll get to that today, because we mainly want to go with 6 types of radiation. Because knowing these will be important to understanding how these different types of applications in the real world work.
Wait, I thought we were talking about Chernobyl today.
We're going to get to Chernobyl at the end.
Okay.
Because we're basically, today we're going to try to go through these 6 types of radiation, and then after that we're going to try to go into nuclear power plants and how they work, and hopefully Chernobyl from there. Okay? So, basically for this, as far as formula goes, like again, right here, if you see gamma radiation, all you're seeing is excited state to lower excited state. So, just keeping that in mind for gamma radiation. Now, I mentioned this earlier. Positron emission. This is where things get weird. So, this is almost not necessarily the full opposite of beta radiation, but it's close to the opposite here. So what you get from positron emission, let's talk about this word positron. What is that? What do you think that might mean, just from the word itself?
It's giving off a positive charge.
So giving off a positive charge. So I think that's a good way to kind of start thinking about this. So let's talk about this for a second, right? Positron sounds a lot like an electron, right? But you've got the positive side on this one. So this is kind of the part where nuclear chemistry gets really funky, because this is actually a positively charged, it's a positively charged electron.
What?
Breaking the rule.
Yeah, exactly. That's why it starts getting weird with nuclear chemistry.
So they're trying to.
And we also call that antimatter.
So it's still called an electron now?
No, so it's called a positron. It's just our description of a positron is a positively charged electron. It's like an electron, except it just has a positive charge. So the process by which this happens is kind of like if something happens in a nucleus to split apart into a positive and a positive charge and electron, this is kind of the reverse of that, where a proton is converted into a neutron. So if you think about that, if a proton is converted to a neutron, we're going to have a neutron and then this extra remaining positive charge left, and that's what the positron is. And so that gets emitted from the nucleus, just like in beta decay, just with the positive charge instead of the negative charge.
Unfortunately, there's not a Hobbs definition that works.
Yeah, it's
that one. Okay, it's just kind of a crazy thing that the whole idea of antimatter is a crazy thing. Now, according to classic physics, anytime matter is created, there's always an equal amount of matter and antimatter. Antimatter is just the opposite of the matter. That's what the anti is. So a positron is a positively charged electron. You have an antiproton. What would that be? A negatively charged proton. So you can have antihydrogen, which would have a negative proton with a positive electron going around it. Okay? It's kind of like the alternate universe type thing, you know? But when matter and antimatter collide, they annihilate one another and produce a ton of energy. Now, if any of y'all are Star Trek fans at all, okay, the Starship Enterprise is powered by a matter-antimatter generator, okay, to where they allow the matter and the antimatter to collide, produces energy, and that allows them to go warp speed. Now, the reality is we don't have that. One of the issues with the Big Bang Theory is that there was this big explosion, tremendous amount of energy. From all of that energy, all of the matter was then created, E equals mc squared. Okay? Well, if that's the case, there ought to be equal amounts of matter and antimatter in the universe. And there's not. Where did all the antimatter go? I mean, that's a big question that science is still trying to figure out. So, matter and antimatter. Antimatter is a really weird thing.
Yeah.
Go ahead.
So yeah, I mean that's pretty much a good explanation of that. Let's talk about the C here. So if beta emission was from neutron-rich elements, what do we think this positron emission is going to be from? Not neutron, not electron.
Proton.
Remember what's happening, right? We're having a proton converting into a neutron. So what does that mean about the element? What did it need?
Oh, it needs neutrons.
It needed neutrons, right? So so the element that's a positron emission would be a neutron what element? Neutron light, or neutron
Yeah, like
light.
not enough.
So neutron deficient is what we're going to use, right? It needs neutrons.
I
So
don't
we
know
have
what
neutron
that
rich, which is like, I've got too many neutrons to deal with, and then neutron deficient, which is I need some neutrons. I forgot how to spell efficient. let me just look real quick.
Just do neutron not.
Neutron not. Probably better to use definition or proper terminology here. There you go. So neutron deficient. Yeah.
Okay, so Mr. Sloss,
C-I-E-N-T.
antimatter is just like negative matter. Like,
Is that what
That's a hard question to answer for me. It's essentially, it's not necessarily that it's negative matter, it's just the opposite of matter.
It's not, it's just the opposite of whatever particle it is. It's kind of like the evil twin.
Yeah.
Okay?
that makes sense.
Wait, how is that even like formed?
Yeah, that
I mean,
starts going
like-
into quantum and
I
physics.
mean, it's just,
It just
That's
there.
not bad.
it
It just
just
is.
does. I mean, to be honest with you, it makes no
Okay.
sense to me
Yeah.
either, so.
Especially when you get like, you'll find out that like a lot of stuff just like doesn't make sense sometimes in science. When you get into stuff like the quantum realm, and all that other
I
good
can't
stuff.
help myself, I gotta read this story.
Oh, is there a story in the book?
Well,
or is
what
it-
is this always being written into?
In an
Scientists
old
just like, it is what it
It pretty much, honestly, like it's
In an
hard to
old
explain.
This is,
What?
Antimatter is weird. Even like physicists with PhDs, like they kind of understand what's going on, but even then, like there's so much science done on just quantum physics and stuff like that because a lot of people still have no clue what's going on.
That's the stuff in Amsterdam.
And it's also kind of the stuff that kind of fuels the science fiction that we see today too. I mean, like Mr. Hobbs mentioned, Star Trek has that matter-antimatter reaction that powers the ship. You'll see a lot of that Ant-Man, like exploring into the quantum realm and it's like time travel through the quantum realm because quantum
I didn't
physics is
understand
weird.
that part. I like the movie, but I didn't understand all that.
Also, then,
Yeah, what about Back to the Future?
Back to the Future, I don't know what, I can't remember what exactly they used. I mean, they used the flux capacitor, but the flux capacitor is just nonsense.
they had to have, and by the way, there is a classic cult video movie called Buckaroo Banzai Across the Eighth Dimension, okay? Which Buckaroo Banzai is a nuclear physicist, a brain surgeon, a race car driver, the lead singer in a rock band, and a world superhero. And I think I'm leaving off something, okay? So very talented. But his physics experiment was he was able to penetrate the inner space of matter, since most matter is empty space. And he went in there. And the vehicle that he used was a souped-up Ford Ranger. But this movie came out before Back to the Future, and it had Doc Brown from Back to the Future in it. Okay? And they basically had the flux capacitor in that vehicle there, too. So Back to the Future kind of stole it from that movie. It's a classic movie if it ever comes on. Buckaroo Banzai Across the Eighth Dimension. It's got Jeff Goldblum, the Jurassic Park guy, the Independence Day guy. Okay, he's in it. Peter Weller, who was the original RoboCop, was in it. I mean, it's star-studded cast for a stupid movie. All right, new discoveries of subatomic particles. The discovery that all atoms were made of just 3 types of particles showed a great simplicity in the structure of matter. Unfortunately, this simplicity was soon proven false. In the decades following the discovery of the neutron, scientists discovered more subatomic particles. These particles were not stable. This is the part that gets me. They did not exist in ordinary matter. Instead, they turned up when atomic nuclei were struck by high-energy particles of radiation. A target nucleus would shatter, giving rise to one or more new particles. Such collisions happen very infrequently in nature. In order to have more collisions to study, scientists built cyclotrons, synchrotrons, and linear accelerators. These big, long underground tunnels where they get the particles, subatomic particles, going super fast, near the speed of light, and smash them into one another. The one that's working right now, the latest and best, is called the LHC, the Large Hadron Collider. And it's in CERN, Switzerland. It's actually a 23-kilometer circle underground, and it goes through like three countries. I think Germany and France and whatever, all right there by Switzerland. Okay? And they just smash particles together.
Wait,
Okay?
so why did they do that?
Just to try to discover, that's how they make new elements, and that's how they try to discover the subatomic particles.
So they're just...
That's also one of the ways that bombs, like that, when we go into hydrogen or atomic bomb, that's one of the reasons why atomic bombs works, because what happens is you smash a neutron into uranium-235 and it causes this
I
reaction.
feel like there would be so much more use of the money.
Yeah. Oh yeah. It was billions and billions of dollars to build that, but there were like 21 countries involved.
Yep.
So these machines differ in the manner by which the particle, quote, bullets are accelerated. As a result of these new tools, however, blank numbers of new subatomic particles have been discovered. How many do you think? 10, 20?
However many are in white outline letters.
Those are new elements. We're talking about subatomic particles, things that were theoretically in the nucleus.
Oh, it's probably.
Hundreds
Yeah.
of new subatomic particles have been discovered. This huge family of particles can now be explained in terms of more truly elementary particles. Physicists now refer to two families of particles. The first, the leptons, include the electron, the mu meson, which we affectionately call the muon, okay, the tau meson, and three types of neutrinos. Each neutrino is matched to each of the three particles mentioned. Neutrinos have no charge and no detectable mass, yet they're considered a particle. Okay?
It sounds made up.
I know. Okay, neutrinos have no charge, no detectable.
Yeah,
These
like a
six
story.
particles are grouped as a family because they are affected only by the electroweak force. This is a force that affects charged particles only in the nucleus and is involved in certain kinds of radioactive decay. Leptons seem to be truly elementary. No evidence yet exists that leptons are made of smaller particles. So the electron has never been able to be split into anything smaller. Okay, so maybe it's one of the smallest particles. But wait, there's more. The second family of particles is called the hadrons, Large Hadron Collider, LHC. These particles are affected by the strong force that holds the nucleus of an atom together. Hundreds of hadrons are known, including the familiar proton and neutron. These particles are not elementary. Physicists have proposed not proven, proposed, but they all talk like it's proven. Physicists have proposed that hadrons consist of smaller particles called quarks. The six types are, quote, flavors of quarks are called up and down, top and bottom, which are sometimes called truth and beauty, and strange and charm. These guys have spent way too much time in the lab, okay, getting way too familiar with their neutrinos and their quarks. They're a little quirky, all right. These, the six types or flavors of quarks are called up and down, strange charm. Each type of quark can have one of three colors. These are not colors in the normal sense, but they're more like a kind of charge. Up, top, and charm quarks have a charge of plus 2/3. The remaining three quarks have a charge of minus 1/3. So the proton is made up of two up quarks, 2/3 and 2/3 makes 4/3, and a down quark, which is a minus 1/3, brings it down to 1. The neutron is made up of two down quarks, negative 1/3, negative 1/3, which is negative 2/3. Very good. This is an advanced class. Okay, and one up quark, which is plus 2/3, goes to 0. Okay. So, protons and neutrons are made up of smaller particles called quarks, and they have kind of some of those things all right up in here, and on the anatomy of an atom back there, right? You know, they see quarks right in the middle.
Isn't that a little game Scrabble?
Yeah.
I feel like these people just found random letters, like made up words,
Okay.
and we're like, these are the words we're using.
All right, now this is where, now you thought that was just crazy. This is where it really gets crazy. This is why I have to read this. Each lepton and quark, leptons are the electrons in those, and each quark has a corresponding antiparticle. For example, the anti-electron is called the positron. It has the same mass as the electron, but a charge of plus 1. Now, the anti-down quark, not to be confused with the up quark. This is the anti-down quark, has the same mass as the down quark, but the opposite charge and color. When a particle collides with its antiparticle, both are annihilated, a burst of energy is released, and new particles are formed. The study of the forces within atoms is equally important and fascinating. Physicists have identified that the particles that carry atomic forces, the photon, which has no charge and no mass, carries the electromagnetic force. So that's how all light is, energy is carried in little packets called photons. We'll talk about later on this year. Okay? Other particles called bosons, they carry the strong and weak force mentioned earlier. They just, just bosons. They just carry the forces around. Okay? The massless particles that carry the strong force holding quarks together. What would be a good name for the massless particles that carry the force that hold everything together?
Glue. Gluon.
They're called a gluon. Okay, a gluon. Creative names. Those that carry the weak force are known as the W plus, W minus, and Z particles. Unlike photons and gluons, these particles are very heavy. Their mass is as much as 100 times the mass of a proton. Now, here's my dilemma with this. Okay? How can you have a subatomic particle that's 100 times the mass of a proton or a neutron, yet it's not figured into the weight of the atom, you know? It only exists when you blow the atoms apart. So here's my question. You get a grand piano. They say that usually the studying of an atom is like taking a grand piano and throwing it down a flight of stairs, watching the pieces that fly off, and then trying to figure out how to play it from that. Okay, it's a pretty crude method of understanding the atom. Smash it, see what comes flying off. Okay? So, as you throw that piano down the stairs, a sliver of, a piece of wood from the piano comes off. Is that sliver truly a sub-piano part? Now, if it was a key maybe, or if it was a wire, a piano string or something, then possibly. But all these random, so let's just say that it came down and a bunch of pieces all stuck together as it flew down. Is that new bigger piece truly a sub-piano part? So I don't know. It doesn't make any sense to me, because now we have the number of elementary particles has grown. They now include 6 types of quarks, 6 leptons, 24 antiparticles, 8 gluons, the WZ bosons, and the photon. The physicists' hope for simplicity is not satisfied by these numerous subatomic particles. Hence, the search for truly fundamental particles continues.
Okay, what class would you learn this in?
I don't think either of our degrees cover the class you learned this in.
Well, yeah. Actually, no. I did physics of the atom.
Oh, okay. So I
Okay,
never
physics
got-
3 class.
So
Okay.
don't take that.
Yeah.
Yeah, physics
That was
is
a
where-
very rough class. There was only 9 people in the whole school that took that class. It was 8 guys and 1 girl. She was a flashy blonde from Reno, Nevada. Okay? But she was very, very smart. And thank God I befriended her, because she's the one that saw me through that class. Because I didn't have enough math. You really need to have about 4 semesters of calculus in order to be able to begin to understand what's going on here. I only had 2 semesters of calculus. I didn't have linear algebra or differential equations.
I had intro to differential, but it's not.
So anyway, it's very complicated. But the point is, the point is this, is that we're still trying to figure out all of this stuff. When we talk about protons, neutrons, and electrons, we're on the very basic, fundamental levels. Nuclear physicist is going to really try to figure out, break it down, what are these things made up of, how are they held together? Okay?
Never complain.
Yeah. Now, last thing I'm going to say, and then I'm going to turn it back to Mr. Sluss here, is that in nature there are 4 fundamental forces. I think I talked about this. There are 4 fundamental forces. Forces that just are. Number 1, light. Number 2, gravity. Number 3 and 4 are the weak and the strong forces that operate within the nucleus. Because the nucleus ought to blow apart. Okay? All those protons, all that positive forced into the same place, it ought to blow apart. But physicist says, man, they don't. It must take there must be a strong force holding it together. So we're going to call it the strong force. Okay?
Finally, they did something.
Yeah. You know, they found some other kind of force that works, but it's not quite as strong, so they called it the weak force. And they just are. There's forces that just there that must be there. Now, again, I shared this earlier, but this is a personal belief, but the Bible says in Hebrews that it's God that holds all things together by His Word. I believe He's a pretty strong force. Okay? So, as a result, science, though, is not allowed to use supernatural. The guy can't do that, because the whole point of science is to explain the natural with the natural. Okay, so you can't just say God did it, that's cheating, you know, in the science world. So you say instead, ooh, there must be a strong force holding the nucleus together.
So the strong forces, there's like no equation behind it, it's just the strong force.
Right. Now, I'm sure there's some physics behind it somewhere, but it's way over my head.
Exactly, and a lot of this stuff is just like, you know, it's stuff that's used in higher level chemistry, or higher level like physics and chemistry, because that's when you start really getting into theoreticals and theorizing based on what you know from previous classes. So it's kind of like, the definition of quarks and stuff are kind of like how we use physics equations, right? So do you all know like the speed equation, where it's like Isaac Newton, he discovered gravity and like figured out how acceleration works and stuff like that. So that works on Earth. Then Einstein came up with his theory, which works for everywhere else except for black holes. It doesn't work in black holes, and they found that out recently and made a formula for black holes. Now, do you use the formula for black holes to tell me how fast a ball drops from the top of a...
You'd have to use whatever it's called, the little times 10 exponent.
Well, yeah, you would just use what we've been using for Isaac Newton, right? Like, we can use the general we have what we need, right? And so that's why we kind of cover this and kind of go into that, but we have what we need. We know what a proton is, we know what a neutron is, know what an electron is, and we know how they interact. And so we really only need that, but it's interesting to kind of go deeper and to just kind of see that all this theoretical stuff is still unknown. But again, really, we're working with what we need in order to explain what we need to, and then the further you go up in theoreticals, the more stuff makes less sense.
So, I was gonna say, is a positron just like cancel out one of the electrons? Is it?
Well, if they ever
If they ever collide,
they
yeah.
annihilate each other.
Yeah, they were fine.
Okay, so you can actually make, there's a thing called a bubble chamber.
I mean, 11.
Okay, it's a piece of equipment that's been, I've never seen one, but I've seen articles about them. But y'all listen,
What?
a bubble chamber, you shoot x-rays into the bubble chamber. And in that bubble chamber, the x-rays are converted into matter. It makes an electron which spins towards the positive side of that, and then it makes a positron that spins to the negative side of that. But then they spin and they come back together and then just give off another burst of energy. So it's, the electron is right on the edge of E equals mc squared. You got energy, you got mass. They're related to one another, but on the mass side you have the electron, and we're going to learn that on the energy side you have the photon, and they're kind of right on the borderline between energy and particles. It's that crossover point. It's confusing. You just have to accept it. Just accept it. Don't try and understand it.
And especially for earlier, like, especially in sciences where we're just trying to use what we know in order to do this. Sometimes you just gotta accept some scientific concepts, and then if you're ever interested in those scientific concepts, that's when you get into theoreticals, and that's when we're talking about quarks, and that's when it takes a master's degree to talk about what you think is happening. And it's all sorts of crazy. So, with that side, that tangent aside,
Does that mean me too?
that's what a positron is.
Sorry.
Hey, no, it's a really interesting story. I think it's cool to kind of talk about that every once in a while. But let's talk about how we use the positron, right? And how we use this for this nuclear decay formula. So let's take chlorine here. So it's 918 element of chlorine. Sam, if you remember, the only stable isotope of fluorine is what?
18.
918.
Bro,
I forgot.
Bro, you
I thought it was
19.
I swear.
19. No, it's 19. Yeah, you told me 19 in your video.
Bro, that's what I meant. I was testing you.
You testing me. Gotcha.
Yeah.
Sure.
That's what happened.
Sure.
Yeah. Okay.
For
So
sure.
we know that this fluorine is neutron deficient because the only stable isotope is fluorine 19. Okay. So what we have is beta emission or a positron emission,
What?
which again is like beta emission, but again it's a positron rather than an electron. So we use beta plus. Does that make sense? I'm having to note that. Basically, just you're looking at what you're emitting with beta emission. If you're emitting an electron,
Okay, so it
beta
leaves
minus. If you're
one,
emitting a
okay.
positron, beta plus. Right? And then we have our electron here, which is actually positive, so we use 1, 0 rather than negative 1, 0. And then we have this oxygen here. So again, why is it oxygen? What happens to this fluorine?
It loses
Like,
protons.
It loses a positron, right?
Oh,
Yeah.
So it loses a positive charge. And remember, definition is what happening here is we have a proton that's converting into a neutron and this positron, right? So we lose one proton, which means we lose one number here. And the mass number doesn't change. Again, why does the mass number doesn't change?
Because
The
it's
same
kind of
mass.
like the same weight.
Yeah, the same weight. Again, just like the beta emission here, it's this proton and neutron are effectively considered the same weight here. So even though we converted from a positive 1 charge to a 0 charge, our weight hasn't changed with this beta emission. So different element, same weight. Well, not technically same weight because again, we know that neutron's a little bit more than a proton, but we don't really care about that too much because it's not a big difference. Anyways, so let's try to do this one on the bottom right here. We have copper. This is 29 and copper 29 and 64. I don't know. Well, y'all can see it in your notes. So we got this copper 29, 64. We're gonna have a positron emission that occurs here. What do we need in these two blanks right here?
0, 1E,
0, 1 E for a positron emission, right?
and then 64, 28, which is nickel.
64, 28, nickel. Yeah, I wish I knew enough references to Nickelback to make jokes about them, but fortunately I don't.
Oh, I thought he was gonna like spin one off of that.
No. Like the only thing I could know is like graph, the graph meme, and you know if I had a graph up, I could pull up the ratio and be like, look at this graph. You know that meme. I feel like half of y'all have seen that meme. Anyways, have you not seen that?
No.
It's Nickelback, and he has a picture, and it's, look at this photograph, but it cuts out the photo, so he just says, look at this graph, and it's a graph of, I don't know what it is, but he's just smiling. It's really good. It's very good. You should look it up. Just look at this graph.
Oh, I'm
It'll
good.
make you laugh, almost
We are
guaranteed.
lunchtime and a
Anyways. Anyways, I didn't even think I was going to make a joke about Nickelback today, but sure enough, here we are. Does it make sense for everybody for positron?
Yes.
Alright, let's move on to electron capture. So this is like the actual polar opposite of beta emission. So this is kind of like, it's weird because this is like the reverse and electron is like the opposite. It's the electron capture.
Wait, the reverse and the opposite aren't the same.
Yeah, I know, it's weird. So basically with electron, so think about it with positron versus beta emission. When I say reverse, it's basically instead of a negative charge being emitted, you have a positive charge being emitted here. So this is the exact opposite because what happens if you have an electron that gets captured into the nucleus. So it's like the polar opposite of beta emission. Sorry, it's confusing because it's like they're both kind of opposite, but
Yeah,
they're
we
own
have to
respective
remember all
ways.
this.
How is electron get into the nucleus?
So it's a low energy electron, right? So let's look at the electron shells, and this is something we'll go into. And some of y'all did new projects with electron shells. The example that I remember seeing is, and I think it's in the PowerPoint when we ever send it out, is beryllium here. So we have beryllium, and if we're looking at electron shells, this is something again we'll learn later. But you've got 2 electrons here, and they have this outer shell which has 2 more.
I was falling sick in English.
Because again, beryllium has 4 protons, so it has 4 electrons on it, right? So what happens with electron capture is that one of these electrons in the lowest energy level comes into this nucleus and converts itself into, I believe,
A neutron? I mean,
it's not a neutron, I think it's a proton. Well, I mean, like, yeah, it's a well,
A proton's converted.
Proton plus an electron.
yeah, proton plus an electron equals a neutron, right? So an electron comes in and melds with a proton to make a neutron. So again, that's what we're talking about.
Evidence of the Hobbs definition.
Yeah, again, that's the Hobbs definition. Going back into it, this is the electron on and off relationship with this proton. They broke up at beta emission, and they decided, you know what, I actually really love you, Mr. Proton, and now they've gotten back together. And that's what happens with this electron capture. The electron from the lowest energy level gets captured inside the neutron and converts a proton into a neutron. Or sorry, gets captured into the nucleus and converts a proton into a neutron.
Wouldn't
So-
that like really mess like everything up, like with the only having one on the one inner shell?
Yeah.
Wait, so
The other electrons will shift and adjust,
Yeah.
but we'll make it an ion.
It will make it an ion, it's just weird.
wait, it's the electron and proton that makes the neutron?
Yep, electron and
Okay.
proton.
I consider it the Venus flytrap of nuclear radiation, where it's just kind of there, and then all of a sudden, an electron comes, gets too close, sucks it in.
How does it get there?
Oh, so it becomes a different isotope of a different element, a smaller, it goes to a smaller element?
Bigger, actually, because.
Bigger.
Bigger.
No, you're right, smaller, because the proton's turning into a neutron, so you're losing a proton.
Yeah. So less positively charged, basically. It's like basically canceling out charges here. Like this is one of the electrons decided to cancel out one of the charges with proton. Because again, they wanted to get back together and now they're a neutron. So that ends up making something like that. So that's kind of the explanation for it written out. It's confusing, but you can think of it as pretty much beta emission, but in reverse. So it's beta emission is us releasing an electron from the nucleus. Electron capture is us capturing an electron, pulling it into the nucleus. And then you have positron, which is just positive beta emission, which is weird to think about. But again, I don't really want to go over another discussion of antimatter. So we'll leave it at that. But to fill in the notes for note state is the exact opposite of beta emission, or beta decay. I like emission because you're emitting an electron. So I think the exact term for this one is, this is just describing what type of element wants to go through electron capture. So remember, in electron capture, what is being converted into what?
Then electrons being converted.
Proton to a electron to a neutron.
Proton and an electron into a neutron, right? So is the element that wants more neutrons neutron rich or neutron deficient?
Neutron.
Deficient, right? It needs a neutron, so it undergoes just a different method to do so, which is electron capture. So
So the two weird ones are neutron deficient.
yeah, that's a good way to think about it. It's just that their neutron, they undergo decay in different ways to get their neutron, right? The positron emission uses antimatter and converts and sends out a positron from a proton being split into a nucleus. Or nucleon. No.
Just explode.
Or neutrons. What? These words. You can't talk sometimes. Alright. So, we're going to go to the next part here. So, we're still using this electron, because we're still talking about an electron here, but the electron is going to be on the left side of the equation now because we're adding an electron to the overall, to the nucleus, right? So, it's just making sure to know where you put it in. So, for example, carbon-11. Obviously neutron deficient because we know that most carbon exists as carbon-12, right? So, it goes through this electron capture process. One electron comes in, and you end up getting this boron here, right? Because again, you have a proton being converted into a neutron because the electron's coming in and joining with it. Yeah?
Okay, couldn't it, I don't know, but could it be possible, it was like carbon 14 and it did this, and it was like carbon 15 and it did like the wrong thing? Like what would happen? Or carbon 13, what if it was like carbon 13?
Okay.
And it did this and it became carbon 14, like it did the wrong thing. Would that be possible for it to do like the wrong action? Like the wrong radiation?
Like, are you saying something like an electron would mate with like a neutron, or?
No, I'm saying if it was carbon 13, would it be possible that this
Like
type
they
of
did.
radiation would happen, it would turn to carbon
Do
14 and
electron
add a neutron?
capture.
So if it's saying that this might turn into an electron capture. Well, so the thing with electron capture, it changes the element entirely, right? Because you're losing a proton, it's becoming a neutron, right? So it wouldn't necessarily become another version of carbon, it would be beryllium again, except it would just be beryllium-12, which I don't think this is stable at all, because I think there's only one stable isotope of beryllium. Or no, this is boron, excuse me. Boron-12. Or not 12, actually. It just turns into this, right? Because again, you don't lose you don't lose mass in this process. You're changing a proton to a neutron. Remember, proton and neutrons have the same weight. So you're not losing mass, you're just changing the number of protons, which changes the element entirely. So again, if we're comparing the masses here, 11, 11, same mass, different atomic number.
What's the whole function, purpose, why do things undergo radioactive decay? To become more stable. If they're doing something backwards, they're becoming less stable. Nature doesn't do things to become less stable. They always want to do things to become more stable, get to a lower energy state. So as a result, these radioactive decays are all an attempt to get to that lower energy state. So it's not just going to accidentally gain something, to where it's going to be less energetic. Nature doesn't make that kind of mistake. Okay? So it's always trying to get to the lowest possible energy state, which is why different atoms give off different types of decay. What does it take to get from point A to point B?
Gotcha. Thank you. I wasn't exactly understanding what Sam was asking here, but yeah, that makes. Did that answer your question, Sam? Yeah, essentially, yeah. Nature never wants to go back to a higher energy state. It always wants to start getting more and more stable. That's another concept we'll talk about with entropy at some point, but not right now. So that's the equation here for electron capture. So let's try to do this one here. So we've got Y, which I believe is, I don't think it's yttrium. Am I crazy?
It's
Yttrium. Okay, no, I'm not crazy. It is yttrium. Okay, so we've got yttrium 39, mass number of 88. It undergoes electron capture, and so what isotope of an element we're going to get here? What are we going to get? Strontium.
38 over 38.
Okay, so we get strontium, and you said 38 over what?
88.
88.
Or 88.
Gotcha. Does that make sense for everybody? Awesome. All right, so we'll move on to the last part of this here, which is spontaneous fission. And so this is going to kind of talk about, our what happens inside of a atomic bomb here. So
This stuff is like cool, but it's so confusing.
yes, and that's nuclear chemistry in a nutshell. Because nuclear chemistry is just it's weird compared to normal or electron-based chemistry. But it does explain a lot of how nuclear. It's good to learn these now because when we go over it, you'll kind of see it's like, oh, hey, I know how a nuclear reactor works based on this chemistry now. I know how the nuclear bonds work based on chemistry. I know how chemotherapy essentially works. And it's all because of these types of radiation. So, spontaneous fission. So, what does spontaneous mean? Happens by itself, right? And then fission. What does that imply to you? Fission. Splitting apart. So, essentially, spontaneous fission is the splitting apart of a large nucleus into two or more smaller nucleuses. So. Or two or more. I should probably clarify two or more. There can be two or more. So yeah, and I know I mentioned at the beginning of the atom chapter, it's like you can't necessarily just cut an atom in half. This is as close as you get to cutting an atom in half without actually just, pulling some atomic knife and chopping it. So the atoms can split apart, but obviously it's not just like an even split sometimes. Sometimes it is, sometimes it just depends. And that's why nuclear chemistry is weird. So this kind of, if it happens spontaneously, do we think, so if it happens spontaneously, no, that's a bad logic. I'm just going to tell you this one. So this happens very infrequently in nature. So spontaneous, it happens on its own, but there's not, if there were a ton of elements doing this, the world would be crazy, right? Like, you would be seeing explosions just out of nowhere, everywhere. And obviously, I mean, I don't see any explosions going on right now. So there are very few elements that do this spontaneously, but if it does happen, it happens with, it happens on its own. So uranium-235 and, what is Q? I don't think, I think that's plutonium, I don't think that is. Let me check.
Not plutonium.
What is?
It's not plutonium, I can't remember off the top of my head though.
It's, oh, never mind, I'm sorry. I was thinking you said plutonium. It's plutonium. I thought you said plutonium.
Is it
94.
Yeah, it's plutonium, yeah, okay. I didn't look at the numbers, I should have done that. Yeah, plutonium, okay, cool. I'm not as good as Mr. Hobbs.
So the actual 235 and 239 aren't going to undergo spontaneous fission. They don't. It doesn't happen naturally. So we have to make such unstable nuclei that they do just then blow apart on their own. So when you bombard the uranium-235 with a neutron, it changes it into uranium-236. Uranium-236 is the thing that's going to undergo spontaneous fission. It is so unstable it just blows back apart.
Yeah.
But it doesn't just get rid of the neutron and blow it into smaller ones, and it varies on what it blows up, it breaks apart into.
And then this release at
Where do those neutrons go though, at the very end of
the
that?
neutrons go. So this is kind of how reactors work. This is how nuclear reactors work. So basically, if you got a ton of uranium-235 in your nuclear reactor, all you need to do is just set off this one, right? Because you set off this one, you make this unstable isotope, and it splits into these three. And now you've got 3 extra neutrons that all collide into separate entities of uranium-235, which sets off a chain reaction. And this is why, like, nuclear reactors are so, like, they produce so much energy, because the reaction pretty much covers for itself and creates this giant explosion of energy. It's again also why nuclear bombs tend to be so deadly. There's a lot of energy just happening all together, and it's all going on at the same time.
Just get one neutron and shoot it up. One thing.
Yeah, you just need one to start it.
So how do you get just one?
That is a scientist question. I'm assuming
Do you
they find a way to
remember
isolate it.
how the neutron was discovered?
There's the gold foil experiment, right?
No, that was the
The oil
neutron.
drop, oil drop.
No, that was the charge of the electron. The neutron was the very last thing.
Yeah.
Whoa.
It was, you bombarded beryllium atoms with alpha particles. And when you shot the alpha particle at the beryllium, a stream of neutrons came off. So it's almost like creating a neutron gun.
So it'd be probably more than one.
There's got to be more than one, but you're going to have more than one uranium-235 as well.
Yeah.
Okay? And so you have to have those neutrons supplied, so every atomic bomb has a beryllium core. Because that's the trigger, that's the initiator. Okay? So you bombard that with an alpha particle, which uranium is giving off alpha particles, hits the beryllium, and then gives off neutrons, which then starts the reaction. Then once the reaction goes, then you have a whole bunch of neutrons that, each one produces 3, so 3 then cause 3 atoms to split, which each of those produce 3, so now we're at 9.
Yep.
And then, it goes on and on, it keeps building real quickly, and we have what we call the chain reaction, or the bomb.
So how would they get the bomb, like, if it's just gonna, they have like a divider between this, like, hold it?
They do,
We're
actually.
going to get into that discussion later.
Yeah, there's actually a divider, and when we go over the video for atomic bombs, like you'll see what I'm talking about, where they have a divider.
No,
You probably don't know.
So that's good intuition, though. That's really good intuition. They do need a divider for that before we start, but we'll get to that later. So yeah, this is just the reaction. What happens here? So you get you bombard uranium with one neutron, you get uranium-236, and it splits apart into this bromine. And then LA, which I think is
Los Angeles.
can't remember what exactly it's called. Lantharium. Thank you. So you get bromine in the lantharium, and then you get 3 neutrons, which again continue this reaction and go over and over again. So with plutonium, the neutron, I don't know why we don't go over the equation for plutonium, because it's not even in the normal notes here, but.
No, so it goes into, obviously, what's it gonna make?
Did you have math?
Yeah, we'll start with that, yeah.
Or yesterday? Did you have math today or yesterday? Oh, me too.
Okay, so then that one's just gonna blow apart. Now, the reality is it's gonna blow apart into 2 smaller isotopes, but it's gonna be random. They're not necessarily gonna be the same 2 every time. And so you can really just kind of pick 2, any 2, and it's gonna, you know, that adds up to 94.
Yep.
That's smaller.
So let's do that then. Let's pick 2 smaller ones that add up to 94. What do we want?
24.
Helium, thorium.
Alright, 24 and 50 for 94?
Oh, yeah,
You're kidding.
Oh my God.
44 and 50.
yeah.
44 and 50? Okay.
Oh my god.
So,
Ruthenium.
ruthenium, yeah.
Oh my
Okay, so we got
gosh,
24
what?
here.
Bro, I need lunch. My brain is
And then 50 here, which is going to be 10. Alright.
Oh.
And so, again, remember that we got our 3 neutrons that fly off here, so we just need to essentially distribute these in a good ratio to
Wait, is that?
get to how many neutrons are in each of these? Or I guess
There's a lot of neutrons shot off, like less.
so. Let's start off with figuring out how many neutrons we're gonna have left from this.
19.
19.
Wait, I'm so confused.
Okay, so we have
How did-
240
I don't know.
mass. We have a 240 mass number, right? So how many neutrons does this have? If we got 94 atomic numbers.
Oh,
No, 100,
Oh.
136.
136.
That's probably
Wait a
not.
minute.
Wait, so you
236 minus
do the thing and then you figure out what adds it?
Yeah, 146. There you go.
Because I'm confused on why you would add it. But
So again, we're losing 3 neutrons here, so we've got 143
just seems
neutrons to come to.
draw.
Okay, wait.
I
So
still
why
say
is that 143?
Why is it
Like,
143?
where'd you get 146 and where'd you get 143?
240 minus 94. What is that?
That's one, okay. And
So
then
that's 146, and then minus 3 because remember that 3 neutrons are being split up.
and that would go over to the 44 and R.
So I'm just using this to kind of just give us a scale of what we should write, how we should write these as. So I'm trying to think of the exact numbers we use for these 2. It's a little hard to make these up on the fly, but so we know that bigger elements need a 1.5 ratio, right? So let's just do that. So let's do 44 times 1.5 and 50 times 1.5. It's not going to be exact for all these, but this will give us a good idea of just kind of how we should write the recipes and how to figure out what our math is.
66 and 75.
66 and 75.
That's 44 divided by 2 plus itself is 66.
Okay. So 75, 66, that's 136, 141. So that'll get us 141 if we add these 2 together. So we'll just say that we'll use 76 and 67. Does that make sense? So if we know that, we just need to add those to these. So 44 plus 67, what is that going to be?
44 plus 67, that is 111.
Yep, 111. And then 75 plus 76.
75 plus 50?
75 plus, 76 plus 50. Excuse me. I was looking at the wrong number. Yeah. So 126, all right? So yeah, these are a bit harder if we have those, but again, you don't,
Yeah.
the ones that we actually use here
Oh,
are
no,
just
I
these
was-
2, and like Mr. Hobbs said, it's going to be kind of random which one that will get past it. The most important thing about spontaneous fission is that it creates a lot of energy, and then it creates these neutrons which continue the reaction further. Sam, you got a question? Or you, okay.
Well, I was gonna say
Wait,
before, I got,
you understand
I
that?
had I got 19, because I had like 10 less on the
No?
one, and I had like
Yes.
9 less on the other one.
Oh, gotcha.
Kinda.
Yeah, that's fine.
Kinda.
And you won't be doing too many calculations with this
Don't
spontaneous
really
fission.
get the
It's just,
adding.
it's weird. And again, the main important thing to know about spontaneous
Whatever,
fission is
that
that
button is not
spontaneous
important.
fission, it releases a lot of energy and it creates these neutrons that end up splitting off
I got
and
enough.
causing more and more chain reactions. Sorry, that was a little bit confusing, but does that make sense how spontaneous fission works?
Yeah.
Like, it works because it works. It happens on its own. And
Don't
then,
question it.
Yeah.
You can't question
Yeah.
anything.
in order to get it started, we need to add a neutron to make it to an unstable state where it would spontaneously fission, or undergo spontaneous fission. Because
Did you
these
get
elements
new
aren't
shoes,
known.
Caroline?
You just have to make it to where they
No?
go. And that's what we use a lot in our nuclear reactors and our
There you go, you're watching.
nuclear bombs, etc., etc. Okay? Yeah, and the rest of that basically just goes into D here. So